previous session we have seen the numerical, first numerical on a shaft design. So in that we have seen how to calculate the diameter of the shaft. So in addition to that, there will be the numericals like to calculate the diameter of the shaft on the basis of torsional rigidity. In that case, we'll have to learn. So I'll take same previous numerical, and in addition to that, I'll read here. This is torsional rigidity numerical. For the shaft, permissible angle of twist 3 degree per meter length. 3 degree per meter length. The modulus of rigidity of the shaft 79,300 Newton per mm square. Calculate first the permissible angle of twist theta. Second, calculate the diameter of shaft on the basis of torsional rigidity. This is important. So they have asked about the torsional rigidity. We must know the formulation for the torsional rigidity, which we have proven. That is, we know theta is equal to 584 MTL by GD raised to 4. So this is nothing but the torsional rigidity formulation which we'll have to use. Now they are asking firstly calculate the angle of twist theta. But before calculating this angle of twist, we'll have to consider the statement. What they have given, read it carefully. For the shaft, permissible angle of twist 3 degree per meter length. Now in previous numerical you can see I will have to calculate here the theta first, because they have given 3 degree per meter, so it is in mm, 1000. With respect to length, in previous numerical the length is given with respect to bearing center to the pulley, they have mentioned 150. So if you calculate this, you will get the value of theta, it is in degree, that is 0.45 degree twist will occur. Correct? So this was the step number 1, you can write. Now first whatever they want we have cleared. Then shaft diameter. This is the equation. I'll put D is equal to, it will give me 584 torsional movement with respect to length of shaft divided by G theta. So D raised to 4 you will have to convert like this, and length, the length of the shaft is nothing but it is the distance. So here L is nothing but 150 as like a previous numerical. So by putting this we'll get the diameter, it is in mm. So this will be the different as compared to the solid shaft. Previously we have calculated 46 point something, that we have taken 50 mm. Now right now just do the calculation. Torsional movement we are having 1193662 into length 150, G modulus of rigidity they have mentioned, that is 79,300, and the value of theta, here theta 0.45 degree. So after putting this I'll get the value 41.38 mm. So I told you I can write it is nearly approximate equal to 45 mm for the shaft case in case of the torsional rigidity. So this kind of the simple numerical is there. They will ask. So we'll move toward the numerical number 2. So I'll read and simultaneously I'll write the data. A transmission shaft is supported on 2 bearings which are 1 meter apart. So it is very clear that from my point of view that 2 bearings are situated at 2 ends. So I will have to draw 2 bearings which are 1 meter in apart. So I can say the bearings 2 end, left side and right side bearing, okay, 1 meter 1000 mm distance. Power is supplied to the shaft by means of coupling. Okay, power is transmitted from the shaft by means of belt pulley which is having 250 mm diameter. Belt pulley is situated over there having 250 mm diameter, okay, which is located at a distance of 300 mm from left hand bearing, which is situated 300 mm from left hand bearing. What it indicate? It indicate that 300 mm from the left, it means 1000 minus 300, remaining is 700. So I will have to draw the diagram. So this is first of all I'll draw pulley. Correct? Now they have suggested us we'll have to calculate the bearing. So this is left hand bearing with the center, and they have told us this will be the distance 300 mm. Okay, so now total bearing length is 1000, so remaining is like this. So here is the bearing, and this distance they have suggested us, this is 1000 mm. So remaining is here, from this end it is 700 mm. So this is very clear. So I will have to draw side view for my understanding of the diameter of the pulley and all. So I have drawn this. So of course at the center. Then what they said next, the ratio of belt tension 2:1. Okay, but I don't know right now it is vertically acting downward or horizontal. So tension act vertically downward, important, vertically downward. So of course pulley is situated over here. So tension on tight side P1, P2, self weight of course W, which is equal to M into G. Clear? If they have not given self weight of the pulley, we will not take. We will take 0 if they have not given in the statement. Understood? So here we have calculated the things, and they have mentioned the pulley diameter 250. So pulley diameter 250, I'll directly write radius 125. You can understand this. It means the diameter is 250. Okay. Then the shaft is made up of steel, of course, yield strength 300 Newton per mm square, and factor of safety 3. Determine the diameter. Of course, diameter we need to calculate if it transmits 10 kilowatt power. So given data, power 10 kilowatt at 360 rpm. 360 rpm. So these are the things which we must know, and the remaining things, what is remaining in this. So whatever be the things are, I have I have drawn in this diagram. So now remaining is the diameter of pulley. I'll write diameter of pulley, capital D. How much? It is 250 mm. Why capital D? Because we have considered small d for shaft. Then weight they have given, that is 20 kg. So I will have to write W. What they have mentioned? Basically the mass of pulley, not weight. So mass is 20 kg. Correct? So anything else? Yes. Tension on tight side to the slack side. They have mentioned 2:1. So I can write this P1 is equal to twice of P2 directly. Clear? So I don't think anything remains. So every thing in this statement, whatever they have mentioned, I have put over here. So we'll start the step-by-step procedure. As per the step number 1, we'll have to calculate maximum permissible stress. So that is equal to 0.5 times SYT by factor of safety. So the factor of safety they have given 3. Yes, I forgot to write here. You can write FOS 3. So by putting the value, you will get the maximum shear stress occur in this structure is 50 Newton per mm square. You just put the value. Now there is no need at this level, so I'll write the values and all that. You can get it. You just find out the value where maximum shear stress tau max. Then step number 2 is to calculate the torsional moment MT question mark. So to calculate the MT value, as we know, I'll directly write MT is equal to, that is 60 into 10 raised to 6 into power divided by 2 pi n. So here you can see this is known 10 kilowatt, RPM given 360. Now we'll get easily the value of MT. So just try to find out Newton mm. So this value you just tell me or try to find out. Alright, that is 265 into 10 raised to 3. I'll directly write. You can write 265, 1, 2, 3, whatever it may be. Exactly is 265, 258. So So I have directly mentioned 10 raised to 3. This will be the step number 2 for this case. Now in this we'll have to use the belt tensions. Belt tensions, because it is related with the torque of the belt pulley. So this is P1, P2 belt tension. They have mentioned the ratio, that is P1 by P2 is equal to how much? 2. So I will have to write that is P1 is equal to twice of P2. So that will be the things. Now while doing this, I know I have calculated MT is equal to P1 minus P2 with respect to radius of the pulley. Now P1, P2 we don't know, MT we know, R we know, that is 125 mm. Now P1 and P2 slack and tight side ratio they have mentioned. So I will have to put this value here. I will get directly 2P2 minus P2 into radius, that is 125, which is equal to MT 265 into 10 raised to 3. So here through which I will get first of all P2 tension on slack side. Okay, here I will get the tension on slack side, that is 2122.3. Just check it from your side, and directly by the multiplying I will get the tension on tight side, that is 4244.1. So this will be the tension on tight slack side and tight side. So that we have calculated as per our step number 2. Now we'll move toward the step number 3. What step number 3 is suggested? To calculate the total load. So total load acting on a shaft. Total load acting on a shaft. So it is equal to tension on tight side, slack side, W. So I'll write P1 plus P2 plus W. W is nothing but mass into gravity. So mass is given, iti, how much? 20. So multiply by the gravity, we'll get the total load. So I'll write the total load. You just find out the total load is 6562. 6562.5 Newton. So this will be the total load. For this case, I will have to use the total load, and according to that I will have to calculate the bending moment. That will be our step number 4. The bending moment MB is equal to question mark. See the structure carefully. Now here rule of bending moment is very important. In the numerical, maximum hurdles comes at bending moment calculation, because the remaining things are common. So for bending moment, you can see the structure what I have drawn carefully. So for that bending moment, I just see on the structure, this is pulley, correct? So force is acting, total force 6562 here, 6562 Newton, correct? Total force. Now bending moment I need to calculate. Of course, now while calculating the bending moment, I will have to select which end, which will bend. So see, 300 is the distance from the left hand bearing. I'll say A bearing, I'll say B bearing, right side. Now while calculating the bending moment, I will have to consider 300, but it is the shortest distance. But in case of the shaft with respect to bearing B, it is having 700 mm distance. So bending will occur only when distance is more, correct? At a short distance bending will be there, but it requires more load. So right now we'll have to calculate the bending moment, that is 700 mm is the distance. So I will have to take a distance 700. But before that we have attached bearing A, bearing B, both the end, which will take a load that we call it as a reaction force, balance force they are doing. Now see, this is acting belt, this is pulley which is acting downward. So of course reaction force is upward, which will helps to balance. So I can say reaction at A, reaction at B, RA and RB. This will be the bearing. Now it's challenging part to find out RA and RB. Very much important. So we have decided we can calculate both, no issue. RA and RB also. But we require RB because this will gives me the perpendicular distance for the bending moment at the longest side. So I'll take movement with respect to A, bearing A. How? So I'll take this condition RB upward, that is negative from my point. You can take a positive also, but this is the simplest method. So you can see minus RB into total distance 1000. Correct? Now this force is moving toward the downward. This is upward. We have considered negative. It is positive then. Plus total force 6562 into 300. Correct? Into 300, which is equal to 0. No force is there. Correct? Now through this everything is known. We'll get the reaction force at bearing B, which will be 1968.7 Newton. So this will be the reaction force. So how I can calculate RA? There is no need, but I'll tell you. So RA plus RB, two end force acting to, upward, which is equal and opposite, that is total load. Total load how much? 6562. So RA is equal to, you can directly subtract your RB, you will get Newton. Okay? So this will be your homework. You can calculate from your side. Now our step is, we have reached up to bending moment. So we have to calculate bending moment. Now earlier it was very simple, we can calculate. But right now the bearings are, two bearings are there, and with respect to that we need to calculate. So I will have to say bending moment, which is the longest side, 700. So bending moment at point B. Very important. If it is A, I will have to write. So that will be RB force into perpendicular distance 700. So that will be the bending moment. Therefore I put the value of RB over here. So I'll get, by the multiplying it, Newton mm. I'll directly write the answer. In case of the bending moment, it will give that is 1378104 Newton mm. So this will be the bending moment at B, which is at maximum side. So that will have to select. Now the step number 5. What it shows? It shows that tau max is equal to 16 by pi d cube square root of bending moment square plus torsional moment square. Now we know this, we know this, we know this. Remaining is which is in mm. So here very important is that in such kind of the problem you need to find the bending moment very carefully. Correct? So on the basis of this, diameter is around 52.2 mm. So I can say, as per my method, you can select the in terms of the 5. So diameter is equal to 55 mm, nearly equal to. Correct? So that's all about this numerical. I hope you understood the things. So just my request, you just practice more and more numerical. You will get the ideas, you will get the more types. So no doubt I'll cover here, but understanding the nature of the numerical is very important. Is that clear? Okay, thank you.